Imagine you're training an AI agent to perform a really complex task, like navigating a vast virtual world or writing intricate code. If you only tell it whether it succeeded or failed at the very end, how does it learn what to do at each step? This is the core challenge for large language model agents tackling long-horizon tasks, sparse rewards. Today, we're diving into a paper that offers a brilliant solution to this problem, allowing us to cheaply and effectively evaluate the step-by-step guidance we give these agents. The issue with sparse rewards is like trying to learn to play chess, but only being told if you won or lost at the very end of the game. You have no idea which of your hundreds of moves were good or bad. For LLM agents, especially in tasks with thousands of actions, this makes learning incredibly difficult, often intractable. Existing methods try to generate dense supervision scores for intermediate actions, but evaluating these signals is a mess. It's expensive, often requires full training runs, and makes it impossible to compare different methods fairly. This is where QVAL comes in. QVAL, short for Cheaply Evaluating Dense Supervision Signals, provides a training-free testbed to directly assess the quality of these intermediate feedback signals. The core idea is cue alignment. Think of it like this: a good coach knows which plays are better, even if they don't know the exact score. QVAL measures how well a method's generated scores rank actions according to the true Q values of a strong reference policy, essentially, how well they predict the long-term expected return of taking an action. The QVAL methodology is elegant in its simplicity. First, they collect diverse trajectories in various environments. Next, for each state action pair, they label it with a reference Q value. This Q value represents the expected future reward if the agent takes that action and then follows an expert policy. Finally, they evaluate a dense supervision method by comparing its predicted scores to these reference Q values. They use rank correlation metrics like Spearman's Rho to see if the method's scores correctly order the actions from best to worst without needing any actual training. The results from benchmarking 21 different dense supervision methods were quite surprising. The paper found that simple direct prompting methods, where an LLM is asked to directly output a score or rank actions, consistently outperformed more complex, recent techniques. This suggests that sometimes added complexity doesn't necessarily translate to better signal quality. Furthermore, methods tended to cluster by their methodological family, indicating that the way a signal is generated strongly influences its Q alignment across different tasks. QVAL's findings proved robust across various settings, including different model sizes and whether the target was Q values or state values. However, a significant insight emerged regarding input modality. Methods consistently achieved stronger Q alignment when processing text observations compared to visual observations. This highlights that parsing visual information for value estimation remains a more challenging problem, and the potential additional context from images doesn't always translate to better signal quality in the current state of these methods. While QVAL is a powerful tool, it does have limitations. Its effectiveness relies on having a strong reference policy to generate accurate Q value labels. Also, as we saw, visual observations are still a hurdle. However, QVAL is designed to be easily extensible. This means researchers can quickly iterate on new dense supervision methods, test them without expensive training runs, and accelerate the development of more capable long-horizon LLM agents. It's a crucial step towards making AI agents truly intelligent and adaptable in complex, multi-step environments.